Today, we're tackling a problem that seems simple: sum all elements within every odd-length subarray. The challenge isn't just getting the right answer, but doing it efficiently. Can you find a way to avoid redundant calculations? Given an array of positive integers, our goal is to calculate the sum of all possible subarrays that have an odd length. For example, if we have the array 1, 4, 2, 5, 3, we need to consider subarrays like 1, or 1, 4, 2, and sum up all their elements. The final output is a single integer, the total sum. The most straightforward approach involves 3 nested loops. The outer loop iterates through possible odd lengths, starting from 1. The second loop then picks the starting index for each subarray of that length. Finally, the innermost loop sums the elements within that specific subarray. This repeatedly sums elements, leading to a time complexity of O of n cubed, which is inefficient for larger arrays. Space complexity is O of 1, as we only use a few variables for tracking sums and indices. The key insight for an optimal solution is to count how many times each individual element appears in an odd-length subarray. Instead of summing subarrays, we sum each element multiplied by its count. For any element at index I, it can be the start of I plus 1 possible subarrays, and the end of n minus I possible subarrays. Multiplying these gives the total number of subarrays containing that element. Now, not all of these will be odd length. Half of these subarrays will be odd length, and half even. So, we take the total count, add 1, and divide by 2 to get the number of odd-length subarrays containing that element. We then multiply the element's value by this count and add it to our running total. This approach processes each element once. Let's trace this with the array 1, 4, 2, 5, 3. For element 1 at index 0, it starts 1 subarray, ends 5. Total subarrays, 1 times 5 equals 5. Odd count, 5 plus 1 divided by 2 equals 3. So 1 times 3 is 3. For 4 at index 1, starts 2, ends 4. Total, 2 times 4 equals 8. Odd count, 8 plus 1 divided by 2 equals 4. 4 times 4 is 16. For 2 at index 2, starts 3, ends 3. Total, 3 times 3 equals 9. Odd count, 9 plus 1 divided by 2 equals 5. 2 times 5 is 10. For 5 at index 3, starts 4, ends 2. Total, 4 times 2 equals 8. Odd count, 8 plus 1 divided by 2 equals 4. 5 times 4 is 20. For 3 at index 4, starts 5, ends 1. Total, 5 times 1 equals 5. Odd count, 5 plus 1 divided by 2 equals 3. 3 times 3 is 9. Summing these up gives our result. Adding 3, 16, 10, 20, and 9 gives us a total sum of 58. This is the correct sum of all odd-length subarrays, calculated by cleverly counting each element's contribution. You'll spot this pattern when a problem asks for sums or properties of all subarrays, especially when a brute force approach seems too slow. The cue is often when you can determine an element's contribution to the final answer without explicitly generating all subarrays. The time complexity is O of n, as we iterate through the array once. The space complexity is O of 1, as we only use a few constant variables. This counting trick is powerful. Try the next problem involving subarray sums, same pattern. Don't forget to like and subscribe for more efficient algorithm breakdowns.